Hello everyone, let's analyze. Today we're going to be talking about inner product spaces. So an inner product space is a vector space that has an inner product. So first we should define what is a vector space. A vector space over a field, typically real numbers or complex numbers, is a set that is closed under addition and scalar multiplication. That is to say, a vector space contains all linear combinations of its elements. So a few examples, the typical vector space that we think of is the Euclidean vector space in n dimensions. And this could be over the reals or over the complex numbers. Another example is the set of all polynomials of order n or less. If we sum two polynomials of order n or less, we get another polynomial of order n or less. Similarly, if we scale a polynomial of a particular order, we get another polynomial of that order or less. Of course, if we scale by 0, we get a 0th order polynomial. Another example is the set of continuous functions over a closed interval. Now, we know from previous lectures that this vector space is not complete, but it's still a vector space. Now, for any of these spaces to become an inner product space, we will need to imbue it with an inner product. So an inner product space, we can think of it really like a vector space that has a geometry attached or a trigonometry attached. And I'll talk more about what I mean by that. But let's define what an inner product is. An inner product is a mapping of two vectors from a vector space to a number. A complex number, if this vector space is over a field of complex numbers, or real numbers if it's over a field of real numbers. And an inner product must satisfy three rules. If I take the inner product of a vector with itself, I get something not negative. And I only get 0 if the vector itself is 0. In fact, that's an if and only if. I get conjugate symmetry, which is that the inner product of uv equals to the conjugate of the inner product of v and u. Now, of course, if all of my vectors are real, then I would have symmetry. It's also true that an inner product is linear in the first argument. So we call this bilinear. That is, if the first argument is a linear combination of two vectors, in this case u and v, then we can distribute that inner product to get alpha times the inner product of u and w plus beta times the inner product of v and w. Now, if I have an inner product in the second argument, then I could use the rule above to switch the order and then apply the bilinearity product. But of course, then I get a conjugate in that case. So any mapping that maps two vectors to a number that satisfies these three conditions, we call an inner product. And a vector space with this rule is an inner product space. For example, in Cn, the typical inner product we think of is a dot product, or the product of each entry of u times the conjugate of each entry in v added together. Of course, that's not the only inner product for such a space. Another inner product is if we consider functions that map the interval ab to complex numbers. Then an inner product is given by the interval from a to b of f of x, that is the first argument times the conjugate of the second argument. Of course, both arguments are functions. And in fact, it would be a good exercise for both of these inner products to confirm that all three properties of the inner product space is satisfied. Now, let's get into what we mean when I say that an inner product imbues a geometry onto a space. Well, we say two vectors are orthogonal if their inner product is 0. And this is a generalization of perpendicular. So in fact, we could talk about two functions that are orthogonal to each other. Even though it's weird to think about two functions that are in some sense perpendicular, this idea of orthogonality extends to any space that has an inner product defined on it. Furthermore, an inner product allows us to measure length. We can define a norm of some vector v by taking the square root of the inner product v with itself. And this is called the norm induced by the inner product. So anytime you have an inner product, you have a norm induced by it. Now we say two vectors are orthonormal if they're orthogonal to each other and are unit length. And in fact, sets of orthonormal vectors are incredibly useful and will be one of the main topics of this conversation. Now, just to recall, when we say a norm has three properties it must satisfy. A norm is always non-negative and is zero only if the argument is zero. Any scaling of a vector, that's the scaling can be factored out under an absolute value sign. And the triangle inequality says that the norm of the sum u and v is less than or equal to the norm of u plus the norm of v. Now, to show that the norm induced by an inner product is in fact a norm, we need a property known as the Cauchy-Schwarz inequality, which is given by this argument. That is, the inner product of u and v in absolute value is less than or equal to the norm of u times the norm of v. Note, we should mention that an inner product space is necessarily a normed space because we can always induce a norm, and a normed space is necessarily a metric space, since we can define a metric, that is a distance from x to y, as just the norm of x minus y. Now, let me be a little more clear when I say that the inner product attaches a geometry to the space. We can actually use the inner product to define an angle between any vector or any two vectors in an inner product space. Even if this inner product space is a space of polynomials or functions, we can actually talk about the angle between functions or the angle between polynomials. In Euclidean space, it's kind of natural that we talk about the angle between vectors, but in fact, we can extend this idea of angles using the inner product. If theta is the angle between x and x or y are just two vectors in a inner product space, then the angle between them satisfies the cosine of the angle is the inner product of x and y divided by the norm of x times the norm of y. Of course, that means if x and y are orthogonal, then cosine of pi over 2, right, which is a right angle, is 0. And therefore the inner product is 0. Of course, the inner product is 0 is the definition of orthogonality. So we see that the relationship makes sense. Consider, for example, two vectors x and y that are orthogonal to each other, because our natural idea of cosine originates with right triangles. Then we say that the cosine of theta, according to this definition, is the inner product of x and x plus y over the respective norms, where theta is the angle between x and x plus y. Now, of course, we know that cosine, we typically mean the ratio of the length of the adjacent side, that is the norm of x, divided by the length of the hypotenuse, that is the norm of x plus y. Well, let's see if that works out to mean what we think it typically means. Right, we can distribute that inner product. Notice that the norm of x and y, the inner product of x and y is 0 by assumption, because we said suppose that x and y are orthogonal to each other. And the inner product of x with itself is the norm of x squared. If I simplify, I get the norm of x divided by the norm of x plus y. That is the ratio of the adjacent side to the angle divided by the hypotenuse. And even though in the picture we visualize these vectors as Euclidean vectors, all of our calculations just used properties of an inner product and the norm induced by it. Now, from this, we can see that Cauchy-Schwarz must be true because the inner product of u and v is cosine of the angle between u and v times the norm of u times the norm of v. And of course, we know cosine is between -1 and 1, so if we take the absolute value, we get that inequality. But let's see if we can get a more direct proof without this kind of cosine imbued on our space. Remember that the norm of u is the inner product of u with itself and raised to the 1/2 power. Let's suppose for now that v is a unit vector. Then u minus the inner product of u and v times v, that norm squared is, well, it's greater than or equal to 0. It's property of a norm. We know that that norm squared is the inner product of the argument with itself. So we can distribute. Right, so here we're just using the bilinearity property. Right, we're taking u with this term and this with this term. Then we use the conjugate symmetry property and we expand. So we have the inner product of u and u. Now we know that's the norm of u squared. We have this term minus uv times this term. As I mentioned, this is the norm of u squared. By using conjugate symmetry, this is just the inner product of u and v. And then we can distribute these terms and we get these last two terms. Now, notice that because the norm of v is 1, these last two terms cancel each other out, and we get just this, which we can write as, because this is the conjugate of a number times itself, it's that number absolute value squared. And so that implies the fact that this is greater than 0. That means this is less than or equal to this, because this entirely is not negative. Of course, we could take the square root of both sides and we get this equality here. And so that's true so long as, remember, we suppose that the norm of v is 1. Well, suppose that v is not a unit vector, but it's not 0. Then I can take this inner product and multiply by 1 over the norm of v, right? Using the bilinearity property, we can distribute that and we get v divided by the norm of v, and that is a unit vector. And so because it's a unit vector, this inequality is satisfied. Now, if we multiply both sides by the norm of v, we have the Cauchy-Schwarz inequality. Now, of course, if v is 0, which is the only case we hadn't considered yet, then we just get 0 on both sides. Now, it's straightforward to show that an orthonormal set of vectors are linearly independent. And in fact, this would be a good exercise just to brush up on your linear algebra if you don't think that that's a straightforward idea. And if you do think it's a straightforward idea and you're confident you can show it, again, it would be a good exercise. But when is it a basis for an inner product space? That is, when is an orthonormal set of vectors a basis for the inner product space that it's in? Now, we say that the dimension of a vector space is equal to the number of linearly independent vectors that spans it. But what if the vector space is infinite dimensional? Well, let V be an inner product space. Then if we have a orthonormal family of vectors that is a countably infinite set of orthonormal vectors, then we say it's a complete orthonormal family if every vector in V can be written as this series representation of a linear combination of these vectors. Now, notice that not every infinite set of orthonormal vectors is complete. In other words, if we have an infinite dimensional subspace, it's not enough to just say, look, here I have infinitely many orthonormal vectors. Certainly, this can be used as a basis. I can represent every vector in this space in this way. That's not the case, right? When it is the case, then we call that orthonormal family of vectors complete. Now, by the way, there's an infinity in that linear combination, right? In that sum. So that implies that there's a limit. So when I say U equals this series, what I mean is that the partial sums of the series converges to U in the norm induced by the inner product. That is, U minus the partial sums in norm goes to 0 as n goes to infinity. We typically say that U is equal to the series on the right-hand side in mean. And we'll talk more about that later on in the series. As I mentioned, not every family of orthonormal vectors is complete. For example, suppose you did have a complete orthonormal family. Then in fact, you need every last one of them. Because if you were to remove one, even though you only removed one from infinitely many, right away, that is no longer a complete orthonormal family. If you were to remove just one, it is incomplete. I bet you could prove that. It'd be a good exercise. Now, let's get into a really important theorem. This is the projection theorem. So let V be an inner product space, and let S be a subspace of V. Then for any vector in V, and this is the big space, if I wanted to find the closest vector to U from a subspace S, then it's solved. The closest vector is S star if U minus S star is orthogonal to every vector in S. Now, I hope that from this picture, that's really clear. Now, in the picture, I depicted S as a one-dimensional space, but the idea holds whether S is one-dimensional, two-dimensional, or three-dimensional. If U is not in S, and I wanted to find the closest point to U in S, then I would drop a perpendicular. That is, the line from U to S star, or U minus S star, must be perpendicular to the entire space S. Right? That should be, I think, from the picture, really clear. And if S were a plane, and U were somewhere above the plane, then you would drop a line so that the line was perpendicular to the entire plane. And this holds no matter what dimension S is. So hopefully from this picture, the result or the theorem statement is true. Now we'll prove it rigorously, but I hope that it's very clear from here. Now before I go on, let me just point out that the projection theorem is incredibly important. In fact, if you were to say applied mathematics is jazz, and many people say this, then the projection theorem would be the theme, and applied math would be variations on this theme. For example, least squares method, spectral methods, Galerkin methods. All of these are variations of the theme of the projection theorem. We're always trying to find the vector so that our error or our difference is orthogonal to our search space. Okay, now let's prove the statement. Suppose that, as the theorem says, U minus S star is orthogonal to every vector in S. That is to say, U minus S star, the inner product of U minus S star and S is 0 for every S. Well, let's consider an arbitrary vector in S. Of course, we can see from the picture that the distance from U to S, the magenta line, is certainly longer than the distance U to S star, the red line, right? That's clear to see. Now, the distance from U to S squared is equal to, well, the distance from U to S star plus the distance from S star to S. That's because all I did is I added 0 by way of adding S star and subtracting S star. Now, I hope that you can see that, in fact, this distance squared equals this distance squared plus this distance squared. Right, that's just Pythagorean's theorem. But let's not take that as fact, and let's go through the calculations. Again, the norm of a vector squared is the inner product of that vector with itself. So then we can distribute. Now, all of the cross terms, so when we distribute this term with this term, that's here, and then this last term with this last term, that's here. But the cross terms, so this term and this term, this term and this term, that's here. But notice U minus S star is orthogonal to every vector in S. And well, S star minus S, that's an S. Similarly here. So these last two terms here are 0. Meaning, I get just this top line, which is the norm of U minus S star squared plus S minus S star squared. Now again, this statement from this picture is just Pythagorean's theorem. It's what the scarecrow recites when he gets a brain from the Wizard of Oz. Now, it follows then that U minus S star squared is less than or equal to U minus S, because I'm adding something not negative to U minus S star squared in order to get this. And the only way that this and this are equal is if S minus S star is 0, which is to say S is right on top of S star. And so this proves our theorem. Now, a corollary to this projection theorem, and this is really important because this tells us how to get our hands on S star if we have a basis for this subspace. So let V be an inner product space, and let phi j from j equals 0 to n be a set of orthonormal vectors in V. Then, of course, the span of these orthonormal vectors is a subspace of V. And if I wanted to find the closest vector to U from this subspace, from the span of these orthonormal vectors, then I can do it by specifically this expression. In other words, this is the specific linear combination that gives me the best approximation. The coefficients are computed by these inner products, the inner product of what I'm trying to approximate U and my orthonormal basis. So this gives us a way of actually calculating what is the best approximation. And we calculate it by employing the previous theorem, which is that U minus Sn must be orthogonal to every vector in the span. Now, because my subspace is spanned by finitely many vectors, I have a basis. So this condition here is equivalent to saying that U minus Sn is orthogonal to every basis vector. And the fact that this statement and this statement is the same is straightforward to show. And in fact, this also would be a good exercise, and I recommend it. Now, we're going to replace Sn with its summation representation. And then we're going to distribute. And when we distribute, we're going to take the inner product of U and phi k and put it on the other side, because this minus this is 0, which means these two terms are equal. Again, completing our distribution, we see that this is the sum of Cj times the inner product of phi j and phi k. Now remember, this is an orthonormal family. So if j is not equal to k, I get 0. And if j is equal to k, I get the norm of phi j squared, but the norm of phi j is 1 because this is an orthonormal family. So that implies that ck equals exactly this inner product for each k. And that completes our proof. Now, by the way, I should point out that what if I had a subspace and had a basis for this subspace, but the basis was not orthonormal? Well, then I could still employ this calculation, but at this point here, this wouldn't simplify so neatly. In fact, what this would represent is a set of linear equations that we would have to solve. Our coefficient matrix on the right-hand side would have as entries these inner products. That matrix is known as a normal matrix. But if your basis is orthonormal, then your normal matrix is just the identity matrix, and then this becomes trivial to solve. Now, I should point out that if you do have some finite dimensional subspace S, and you have a basis for it, you can't always, from that basis, create an orthonormal basis. So we can always make an orthonormal basis. That is, if S is the span of A1 through AN, where A1 through AN are linearly independent, which is to say I have a basis for S that's linearly independent but not necessarily orthonormal, then I can actually construct an orthonormal basis, phi1 through phi n, such that the span of both are the same. Not only the same, but progressively the same, meaning that the span of the first k vectors equals the span of the first k orthonormal vectors, where k ranges from 1 all the way to n. So it's not just that I need all phi1 through phi n to span all of A1 through AS, but phi1 through phi k spans A1 through AK. So it's built progressively. One process for doing this is known as the Gram-Schmidt process. So we can actually characterize the Gram-Schmidt process by a fairly straightforward algorithm, but to understand how it works, it helps to see it in action. So let's do that. So here I have two vectors, A1 and A2. They're linearly independent, but not orthonormal. Well, we can start our process by letting U1, and here we're going to call our orthonormal vectors U, by letting U1 equal the normalization of A1. Right, so I just get A1 divided by the norm of A1. So the norm of U1 is 1, right, because I took A1 and I scaled it by the reciprocal of its length. The next thing I want to do is I want to find the closest point to A2 from the span of A1. And from our previous work, we know that that's exactly given by the inner product of A2 and U1 times U1, right? That's a result of the best approximation theorem. Of course, we can also see it from the trigonometry of inner products, because that's exactly the norm of A2 times cosine theta times U1. In other words, the length of this line from here to here is the norm of A2, that is the hypotenuse, times the cosine of this angle. Right? Remember that the cosine of the angle between two vectors x and y is the inner product of x and y divided by the norms of x and y. So then, this dropped perpendicular, therefore, is A2 minus this. And of course, we can check that, in fact, the vector whose coordinates are right here at this red dot plus U2 tilde add up to A2, because it's just this term plus the negative of that term plus A2. So I just get A2. Remember, when you add vectors, you can put them or illustrate their addition by putting them head to tail. So that makes sense. And it should also be clear that U2 tilde is orthogonal to the span of U1. And that's a simple calculation. So now I have two orthogonal vectors. In order to get two orthonormal vectors, all I need to do is normalize U2. So U2 is just the normalization of U2 tilde. That is, it's U2 tilde divided by its norm to get a unit vector. And now I have two orthonormal vectors. So u1 and u2 spans the same plane as a1 and a2. Now, suppose I have a third vector, a3. Now, of course, a3 must be linearly independent to a1 and a2, which means a3 cannot be in the plane represented by this green grid. So let's rotate our picture so that we can see what's happening. So we see that a3, right, it's above this grid. And I want to carry out the same idea. I want to drop a perpendicular from a3 onto the plane spanned by u1 and u2. And I can do that by dropping a perpendicular onto the span of u1. Again, we know exactly the formula for that. And then I'm going to drop a perpendicular from a3 onto the span of u2. And if I take the vector whose coordinates are here and add them together, I get exactly this expression here. And so I'm going to take this vector and subtract it from a3 to get my perpendicular. So u3 tilde is a3 minus the closest point to a3 from the span of u1, this term, minus the closest point to a3 from the span of u2, this term. And that gives me a perpendicular vector to the plane spanned by u1 and u2. And to get an orthonormal vector, I just normalized. And now I have three orthonormal vectors. And those three orthonormal vectors span the same space that a1, a2, and a3 span. Furthermore, u1 and u2 spans the same space as a1 and a2. And u1 spans the same space as a1. So it's a progressive orthonormalization process. This is known as the classical Gram-Schmidt orthonormalization method that is given linearly independent vectors a1 through an. We create orthonormal vectors u1 through un so that the progressive spans are the same. And we can characterize this process by going through each value of k1 through n. Again, we start with u1 by normalizing a1. And for every following k, the new uk plus 1 tilde is ak plus 1 minus. This actually can be described as the orthogonal projection of ak plus 1 onto the span of u1 through uk. And then, of course, uk plus 1 is created by normalizing u tilde k plus 1. So anytime we have linearly independent vectors, we can create orthonormal vectors that span the same space. So now that we've seen the Gram-Schmidt process in action, we characterize it here by this algorithm. Let's continue. Bessel's inequality theorem. Suppose you have an inner product space V and an orthonormal family of vectors in V. Notice that this implies necessarily that V is infinite dimensional, right? It can't be finite dimensional because I have infinitely many orthonormal vectors in V, but not necessarily a complete orthonormal family, just an orthonormal family, right? So this is really important. Bessel's inequality theorem doesn't require that the orthonormal family in question is complete, just any orthonormal family. We see that there's infinitely many of them. Then this series converges and is bounded above by the norm of u squared, where u is some vector in V. So, to prove this, let's let Sn be the best approximation to u from the span of phi naught through phi n. Right? Of course, we know that Sn is the best approximation from the best approximation theorem, which was a corollary to the projection theorem. We also know from the projection theorem that u minus Sn is orthogonal to the span of phi naught through phi n. That is, it's orthogonal to phi L for each L from 0 to n. We also know from previous calculations that the norm of u squared is the norm of u minus Sn squared plus the norm of Sn squared. Again, that's just the Pythagorean theorem applied to this orthogonal picture. And again, I encourage you, as you're taking notes for this, draw the picture. Right? Draw the picture. Now, this implies, since this plus something non-negative is this must be bigger than that. Notice that this is indexed by n and this isn't. Now, the norm of Sn squared is the inner product of Sn with itself. Right? I'm going to replace Sn with its series representation. And by, again, using the properties of the inner product, we can distribute. Remember, again, that this is 0 always except when k equals j. So, right, so then all of this is going to go away except for j equal to k. And so we just get this. So, oh, my apologies, everyone. That should be an n. That is a typo. How dare I? Please disregard the infinite in just this one case. That's an n. The point is that this, right, this term, right, indexed by n, is a monotonically increasing sequence because every time we add terms, these are non-negative terms. So it's a monotonically increasing sequence, and it's bounded above by the norm of u squared for all n. So if I have a monotonically increasing sequence, right, indexed by n, and it's bounded above, we know from previous results of real analysis 1 that it converges. And it converges to a limit less than or equal to the norm of u squared. And this proves Bessel's inequality theorem. Now, if you have some experience with orthonormal sets from linear algebra, you may have expected that we should get an equals here. Right? You should expect that, in fact, these are exactly the coefficients for u in this basis, and this should be equals. But that's only true if this is a complete orthonormal family. And that's the subject of Parseval's theorem. So V is an inner product space. Phi j from j equals 0 to infinity is an orthonormal family. Then this set is complete if and only if I get equality for the expression that in Bessel's inequality was an inequality. Right here we had an inequality. In Parseval's we have equality. Right? So if this is true for every u, then this set is complete. And if this is complete, we know that this must be true for all u. Now, again, from our last proof, right, the Pythagorean theorem applied to our picture says that the norm of u squared is equal to the norm of Sn squared plus the norm of the difference. Now, if we have a complete orthonormal family, then we know that this term goes to 0 as n goes to infinity, which means we can take the limit of both sides as n goes to infinity. Of course, the left-hand side is constant. It's not indexed by n. So I get the limit as n goes to infinity of these two terms. This goes to 0, so I just get the limit as n goes to infinity of this. Now, again, we know from the last proof, we know exactly what a formula for this is. It's this. Right, that was in the last proof. So the limit as n goes to infinity of this is exactly the limit as n goes to infinity of this, which is the definition of a series. So this series equals the norm of u squared. And that completes the forward direction of the proof. That is, if the orthonormal family is complete, that equality is true. Now, if the equality is true for every u, the orthonormal family must be complete. And so we'll leave the only if direction, we'll leave that to you. Maybe you have a weekend, you're not doing anything. You want some excitement. I recommend proving the only if direction. It's tons of fun. So now that we've seen the inequality theorem of Bessel and the equality theorem of Parseval, let's see them in action in a couple of examples. So let's consider the inner product space of continuous functions over the interval negative pi to pi, complex valued, with the following inner product. The inner product that we discussed at the front of this section. Now, by the way, we know that this inner product space is not complete, and that's kind of a problem. And it's a problem we're going to address in subsequent lectures. Now, one can show that cosine of nx divided by the square root of pi from n equals 1 to infinity is an orthonormal family. Is it complete? Let's see. But whether it's complete or not, we still know that Bessel's inequality applies. And Bessel's inequality implies that if we were to apply it to the vector x, or that is the function f of x equals x, that this series converges and is bounded by the norm of x squared. Now, this inner product is the integral from negative pi to pi of x times cosine. Now, cosine is an even function. X is an odd function, and our integral interval is symmetric. So right away we know that that's 0. Because an even times odd function is odd, and the integral of an odd function over a symmetric interval of integration is 0. So Bessel's inequality in the example is pretty straightforward to prove. We get 0 on the left-hand side, and on the right-hand side, we get the norm of x squared, which is the integral from negative pi to pi of x squared, which is 2 pi cubed over 3. So our series on the left in Bessel is 0, and it's strictly less than the norm of x squared, which is a positive number. Notice what this implies. This implies that this orthonormal family, even though it's infinite, it is not complete. It's not complete. Well, let's consider sine. If cosine didn't work, maybe sine will do it. Let's look at the orthonormal family sine of nx over the square root of pi from n equals 1 to infinity. Bessel's inequality again implies that this series converges and is bounded by the norm of x squared, which we have a formula for. Now, to compute this inner product, right, which is the term in our series, again we compute an integral. X is odd, sine is odd. The product of two odd functions is even, so this is not 0. Right? In fact, we could compute exactly what it is. It's a Calculus 1 exercise. It's an integration by parts exercise. I will save you the details of integrating by parts, but we get that formula. So let's investigate Bessel's inequality in this example. In this example, the series of inner products, quantity squared, is, well, it's the square of this term under the absolute value. Of course, the absolute value of this is just 1. So it's really just this term. So it's 4 pi over n squared, 4 pi over n squared. Now, if I factor out the 4 pi, I get the sum of all square reciprocals. And the sum of all square reciprocals is pi squared over 6. This is known as Basel's problem, which we haven't proven, but we'll take it as a given this time. But just to point out that the fact that this converges, this is guaranteed by Bessel's inequality, right? It must converge. The number we get, that's not proven. Again, we're taking it as an identity, as a given identity. Notice that equals 2 pi cubed over 3, which is exactly the norm of x squared. So we get equality in this case. I mentioned that the sum of all square reciprocals add up to pi squared over 6. This is Bessel's problem. But we get equality, right? So remember, Bessel's inequality, it's a less than or equal to. In this case, we get equal. But while we get equality, notice this does not imply that the orthonormal family is complete. Now, if the orthonormal family is complete, that implies equality. But in order to, if we wanted to imply completeness, we would have to show equality for all vectors. And we only showed it for one function, x. In fact, if I were to carry out this exercise for the function f of x equals 1, a constant function, using the same orthonormal family, we would get 0, which is less than the norm of 1 squared, which is 2 pi. So in fact, while we get equality for this function, we don't get equality for this function. And in order to be complete, we'd have to get equality for every function, right, in order to invoke Parseval. So cosine of nx over square root of pi is not complete. Cosine of nx over square root of pi is not complete. What if we combine them? Would that do it? Would we still be missing something? How can we resolve the issue that the set of continuous function on a closed interval is not complete? In order to get to the bottom of this, you'll have to stay tuned. That's all for today.